Hello, everyone. So today we're going to talk about an introduction to modeling and what I'm going to call that, or the type of modeling that we'll start with and that we'll really mainly focus on in the next course, in the second data science course, is statistical learning, okay, or machine learning with a statistical view. And so some of you might have a lot of experience with so-called modeling and may be really interested in it, and some of you may have no idea what the term is or what we're going to go over, and that's okay. I'm going to act like you know nothing and try to build from the ground up. Okay. Now there will be some parts where I may go too fast for some of you, and at the same time probably too slow for others. You'll just have to, if I'm going too slow, you have to kind of stick with me, and if I'm going too fast, then you'll kind of have to contact me and let me or have me kind of fill you in on the gaps. So hopefully that made sense. Now, the material that we're going to talk about in here, some of it is going to be from our current book, R for Data Science. They do talk about modeling, but a lot of the R for Data Science book was about the stuff that we did at the beginning of this course, which was kind of building up to modeling. And so we're going to switch our book focus to a book called ISLR, which is a really popular book for upper level statistics courses in statistical learning. It stands for an introduction to statistical learning with R, so it meets our kind of course perfectly. Now, ISLR, so I'm going to stop showing the slides and go to the internet here. And so if you type in ISLR and then click on the first link, it's going to bring you to this page, which is a page about the book. And if you look up here in the top right, you can download this book for free. Okay, now if you want to, if you love getting books, of course you can get the hardback book. But if not, there's a download a book PDF here. Now we won't ever be doing like any homework or problems out of the book there or this semester. So if you want to wait on getting the book, that's totally fine. But if you're in data science too, I recommend downloading the book, taking a look at it as we sort of go through some of the introductory kind of stuff. And if you aren't going to take the second course, but you are still interested in modeling, I know some of you may be seniors and are just taking this as one of your last math courses, or for whatever reason, this book may be of interest to you because it contains a lot of good stuff. So this is the book that we're going to be using, and I'm also going to take material from another kind of book who goes over the same sort of topics but at a higher level, which is called Applied Predictive Modeling. Now, this book is not available for free, or right now, I don't know if it is or not. I don't think so. And it's more expensive. It's about $80, I think, to get the book. But it is a really good book. I won't make you ever get a book that costs anything for this or the next course. But just if you're interested, know it's there, and I'm taking some materials from it. Okay, so let's get back. And so what we're going to start to talk about in this set of slides is really the language of modeling. So what does modeling mean? So I'm going to use the term the language of modeling, which I took from some courses that are similar to this, but I think it's a good start. You know, what is modeling and what sort of words do we use in modeling? And then I'll go through some motivating examples. This is all about the language of modeling. That's the overarching theme. We'll go through some motivating examples, and then we'll end with sort of a mathematical formulation of what we're trying to do in modeling. And then we'll sort of work off that for the next couple weeks. So what is modeling? Well, a lot of people talk about modeling in different ways. There is statistical modeling. So I'm a statistician, and I think of modeling in terms of statistics in one way. But if you talk to someone else who's a mathematical modeler, they're going to have a different interpretation. So there is a course here, the 300 level, that many of you have taken or are currently taking, called mathematical modeling. And that's going to approach modeling things in a mathematical way. And so a great example of something that you would want to try to model is the growth of COVID-19 throughout the United States or throughout whatever region you want. It's a prime example of a modeling question that you would tackle in a mathematical modeling course, but you can also do with a statistical flair. Okay, but modeling in general, I'm going to define as the process of developing a mathematical or statistical tool to describe the relationship between a set of variables. And I think that's a pretty general definition of modeling that works for us. So, in every modeling question, we're going to have a couple different types of variables. Now, I'm going to call them variables because I'm a statistician, but other people who are interested in data science are going to call them something else. They may call them features, or who knows what else other people call them. Every sort of group of academia or department, for the lack of a better word, is going to define these or call these different things, but they're essentially the same. And since I'm a statistician, we'll call them variables. And then the two types of variables that we'll have are the response, which is the outcome or quantity that we're trying to predict or model, and the predictor. So these two are very statsy words, but that's just what you're going to get with me. The predictors are the variables that we're going to use to model the response or predict the response. So we have predictors and a response. Okay, or we may have multiple responses. We won't really cover that in this course, but you could, in theory, have multiple responses. So you have predictors and responses. And then, why would you want to do modeling, or what's sort of the outcome? Well, there's two types that we'll really focus on here. One is interpretation. And so this is the sort of statistical view that hopefully you had some experience in Stats 1, which I'll say that you have a prereq, but I know not everyone has taken Stats 1, but you have in one way or another in your career focused on interpretation. And when I mean interpretation, I could mean hypothesis tests and confidence intervals. And so those sort of statistical structures are getting towards interpretation. And then the other part, which is sort of more flashy and probably more fun for most people, is prediction. And so I'll also call that classification. Okay, so a classification is a certain type of prediction, but it sort of does a little bit different type stuff. So, but you can basically think of that as interpretation or prediction. And so interpretation, what I mean by interpretation, is understanding the relationship between the predictors and the response. So when I model something, I'm really interested in which one of the predictors has the most, matters the most in predicting the response or modeling the response. So if you're in Stats 2 right now, which I know a bunch of you are, you have a lot of experience, or hopefully you have a lot of experience with this interpretation type stuff. So in there, you'll do a lot of hypothesis tests, confidence intervals, and we'll learn about something that we'll go over in the next few weeks is linear regression. So whatever that means, hopefully you had a little exposure to that in your early career statistics that we should prereq. Okay, certainly you did in my class if you didn't, making a line of best fit is something that will ring in your mind. Understanding how the predictors shape the response in some way is interpretation. So trying to understand that relationship between the two is interpretation, and prediction is predicting the value of the response based on the predictors. Okay, so hopefully that's fairly clear. And the two are not opposites, and they can happen at the same time, but usually your focus is on one or the other. And so here are some examples about examples of some modeling questions, and hopefully they will elucidate or sort of make sense, make my previous statements make sense about interpretation or prediction. So for instance, if I had a data set about emails, okay, and my ultimate goal was determining whether or not a given email is spam, that question is probably going to be purely a prediction question. Okay, so the response is going to be whether it's spam or not, and then I have a bunch of predictors, but I really don't care which predictor. I might, but usually if I'm trying to determine whether an email is spam or not, I don't really care what the predictors are doing and how influential they are in predicting what's spam or not. I just care if my model is good at predicting whether an email is spam or not. Okay, I don't really care about the relationship between them. I just want a tool that when I input an email, it's going to tell me whether it's spam or not. I don't really care about what goes on inside that model. So hopefully that makes sense. And then a second question is determining what type of media will contribute to the most sales. Now, contribute most to sales. Now, this is a question that kind of comes out of nowhere. And so let me give it a bit of context. So if I have advertising data, and actually we'll talk about this data in the next slide, but if I have advertising data and I'm looking at what type of media makes the most difference in advertising, okay, so which type of media, so that could be like TV, radio, or something else, which one makes the biggest jump in sales, okay? This is going to be an interpretation question. So it wouldn't really help me to, it wouldn't really help in answering my question that I have right now here, which one makes the most difference, TV, radio, or whatever. I want to understand the relationship between the two, and not just if I input something and then get something out at the end, which would be like a prediction of sales. So this is an interpretation question. And then I have a third one, determining how much extra a house will be worth if it has a view of the river. And so this would be if you take data about a certain city, maybe in house values, and you have a number of different predictors, where they're located, stuff about the inside, and another predictor could be, does it have a view of the river or not? And so this would be a question where it's sort of interpretation and sort of prediction. So the prediction matters about how much that would be worth, but also the interpretation of that relationship between the predictor and the response is important. So I know that wasn't a great explanation, but hopefully it made some sense. So let's move on. So here's an example, the advertising data. And so the output, or what I'm trying to model or predict, are going to be the sales. So I have an advertisement, I run the advertisement, and then hopefully the sales of that product are going to go up. So that's my output, sales, and we always, or almost always, are going to call the output Y. Okay, capital Y. And then I have different inputs. And so that could be TV, radio, and newspaper budgets. So how much I give towards ads on the TV, the radio, and the newspaper. Those are going to be my inputs or predictors. And so I give each one of those a sort of mathematical variable, x1, x2, and x3, okay? And then I want to find some relationship between x1, x2, and x3 and the output y. And so I can do that. And so here's a picture. This is from ISLR, and they go through that. And it's the sales, on the x-axis, it's each one of the inputs separately, TV, radio, and newspaper, and then on the output, it's y, and what they've done is they've made a line of best fit, or what we'll call linear regression line, through each of the set of points, and so then they'll use that to make some decision, okay, or some output, or they're going to view the question in a different way based on these results, whatever the results are. So this would be what's called a regression model, okay? And as you would know in Stats 2, you may not always want to look at these separately. You may want to look at them together in what's called a multiple regression scenario. If you haven't taken Stats 2, you'll learn about it. If you don't ever take Stats 2 and you're not taking another class, it's still important. All right. Now, a second example that has sort of a different kind of outcome is Fisher's iris dataset. Now, Fisher's iris dataset is a very famous dataset about irises. Okay, and so this is what it looks like in R. It's a fairly simple data set. These are only the first 10 rows, but there are, I think, anywhere from 50 to 250 in different data sets, irises. And so they have 4 measurements and then which species of iris they are. Fisher is probably the most famous statistician of all time, Sir R.A. Fisher. He was also a famous biologist, and so he was studying irises. Now, in this data set, there are 3 types of irises, setosa, versicolor, and virginica. So there are 3 types of species. Those are the 3 types, and then they have 4 measurements on each iris, okay? And the 4 measurements are sepal length, sepal width, petal length, and petal width. So you may wonder, I have a pretty good idea of what petals are, but what the heck is a sepal? Well, here's a picture of the 3 different types of irises. And so the petal is, of course, what you would think of as the petal, okay? Actually, it's probably what you wouldn't think of as the petal. It's sort of the stem from the middle of the flower to the outer part. That's what they're calling the petal, and then the outer sort of thing, what I would think what the petal would be, is what's called the sepal. All right, so there's a good picture to give you an idea of what those are. Now, in this model, or in this kind of situation, the output that I'm looking for is what type of species it is, and then the inputs are going to be those 4 variables. Okay, and so before, in my first example, the output was a continuous thing. It was how much sales there are. Here, it's what I would call a categorical response. So there are 3 different types of species, and I'm trying to predict or model the relationship between the predictors and the response. And so what the type of question that this is called a classification type of problem. And we'll talk about this in a great deal more, but in a classification problem, I'm trying to sort of bin my objects into different bins or classes based on what I see. Okay, so this is actually a very famous classification problem that people have been working on for a long time. And so if you if you don't look at the data, but if you actually look at the irises, you can see from these pictures, if I was going to give you the 4 variables, sepal length, sepal width, petal length, and petal width, give you these variables, give you the numbers, and then ask you, okay, what type of iris it is. If you look at the picture, you can see that setosa looks a lot different than versicolor or virginica. Okay, in setosa, it looks like the petal is very short and the sepal looks really wide. But the two that look more similar are versicolor and virginica. And so here's a plot of the data. And so simple point plot or scatter plot. And then I've labeled the points by their actual species. And so this is actually sepal length on the x-axis versus sepal width. And so as you'll see, you're sort of looking for separatedness, whatever that means. You're looking to see if the points are separated from each other. And it's pretty clear, just as if you looked visually at the actual flowers, that setosa is a lot different from versicolor or virginica. And so classifying a setosa iris looks to be really easy. But versicolor or virginica, there's some overlap there. And so that's where the interesting parts go on. Okay, so there are 2 examples. Now, to get to a more mathematical form, something that may make more sense than what I was trying before, if I have a response y, and it's going to be quantitative, so you may say, well, we just had a not quantitative response in that last problem. Well, I could turn them into some sort of quantitative response. May not be a great idea, but I can do it. I have a quantitative response y, and then I have a set of predictors, and I don't know how many there are, so I said they're x1 to xp, and what we'll actually see a lot in this class is that I'm going to group them all together. You can think of their values each as a vector, and I'm going to put them all together and view it as a matrix. Okay? And so if you haven't taken linear algebra before, this may seem a little bit weird, but you put them together as a matrix, okay? And then you're going to do things with that matrix. Now, we won't ever interact with that. Like, I will never make you do matrix algebra or anything like that, but it's easy to visualize it this way. And so whenever I do it, I'll make sure to be explicit about that. Now, the mathematical form, really what we're looking at is a really simple form. Y equals some function of the predictors plus some error. Okay, and so that function, or the function of the predictors, is called the systematic term. Okay, it's sort of set. Okay, or there's no randomness involved. It's deterministic. The relationship between x and y, and then if we're doing sort of statistical type stuff, which is what we'll focus on, but there is another part of modeling that many people will call maybe machine learning that might not have that epsilon there, or might treat it somewhere different. But that epsilon is what I'm going to call the error term. So that's sort of thinking or believing ourselves that our data was taken with some error. It wasn't fully true, and so we've got to take that into account when we model it. But really what we're interested in is estimating that f. So estimating that function f. And we have a ton of ways to do that. So how do we estimate it? Well, there are a lot of approaches. And so the whole second course is usually, most of it is going to be focused on these approaches of how to estimate that f. Okay, we don't really know the true function. We don't know the truth, but we're going to try to estimate it. And so there's lots of approaches. And in these lots of approaches, there are a bunch of dichotomies that you sort of split up the approaches in a number of different ways. And some of these are really big dichotomies that cut all possible methods that there are, and some of them are sort of more short-sighted. And so I put a bunch of them here, but we can have linear versus non-linear approaches. So are we doing something that creates a line in some dimension or somehow, or is it non-linear? Okay, so are we using something else? And then we could also dichotomize the approaches into parametric versus non-parametric. And so those words mean something to some of you, and they may not mean anything to others. That's okay. There's also a dichotomy of supervised versus non-supervised. And so that we'll get into more of the second course and later on. Supervised means that you know the truth when you're doing the modeling, and unsupervised means you don't really know the truth when you're modeling. And then we sort of have a dichotomy of statistical methods versus machine learning methods. And so lots of dichotomy there. We'll talk about both in this course. I'm going to come towards everything in a statistical view. That's just who I am, but we'll also talk about the machine learning type stuff. And then there's also a dichotomy of regression versus classification. And you saw that dichotomy in my two examples. Okay, and the general approach that we're going to have to any of these problems is that we, one, pick a method to estimate that function. Okay, and it has to maybe satisfy assumptions. Then we're going to let the method learn, i.e. the term statistical learning. They're going to learn from a set of data, and that data is going to be called a training set. Okay, and then after we let the method learn, we're going to test out how the method does on another set of data. And that data is called the testing set. And so we'll talk at length about training and testing data, because that's really essential in modeling. And then the fourth step is we're going to assess the fit. How well did it do? And then we may need to iterate through and try a number of different options, or the same option in a different way a number of times to find some optimal fit. And so that's really an overall approach to learning. I know that was a lot of talking by me, and so I understand if you skipped through a lot of this video or didn't even watch it at all. But hopefully this gives you a sense of where we're going in the course. So at the end of this first course, we're going to talk about that first type, very first thing in all those dichotomies, linear approaches. And so we'll start with the simplest example that all of us know something about, which is linear regression. And then we'll go from there. Okay, so thank you, and I'll see you next time.